right, guys. I think we're finally going to get started. So let a couple more people sit down.
Stragglers.
Okay. So I'm Spoonm, and this is Scape, Matt Miller, either one. And we're here to talk about beyond EIP. As a presentation, we're going to talk less about exploitation vectors and stuff like that, but more about what you do with an exploit. We're going to talk a lot about shellcode, the infrastructure that it takes to be able to do some sort of advanced attack stuff, and then we're going to get into all of those different technologies. So who we are, I'm a full-time student, and I started working on Metasploit for the 2.0 release in 2003. And a little bit after that, Scape came along and was doing a lot of really cool payload stuff, and he joined on working with us in 2004. He's done a lot of the really cool stuff. If anybody's heard of Interpreter, PassiveX, a lot of this stuff he wrote. And he's a software developer, and he just does research for fun. So what's this presentation about? Well, what it's not about, we're not going to talk about any new exploit or attack vectors, and we're not going to talk about any new exploitation techniques. This stuff has been talked about a lot, previous Black Hats, DEF CON's papers, and I mean, there's a lot of good knowledge about there. And we're not going to talk about anybody ODay, we're not going to talk about ODay, bugs. Everything we're going to talk about is bug independent. It doesn't apply to any specific bug. It's going to be able to apply to any bug. So then what we are talking about is what do you do after you can exploit and leverage a vulnerability and start executing code? What do you do after you own EIP? And we're going to talk about some of the different techniques to do it. And by techniques, we're not talking about exploitation techniques. We're talking about shellcode techniques generally. So we're talking mostly about the code that's being run in a buffer overflow attack or any of these sort of attacks. We're going to talk about our tools and the stuff we've been working on. So the plan of attack, what we're going to take is there's a lot of information that you guys need to know. There's a lot of groundwork that allows us to be able to do some of the cool stuff that we do. So we're going to try to start from the basics. We're going to break down and show all of the pieces that make up a payload, how the frameworks, how payloads automatically get generated and things like Metasploit, recent tools, tricks, and different techniques. They're going to allow us to do all of this cooler stuff. So then once we sort of lay that foundation, we're going to move into post-exploitation tools. And that's the term that we've coined for sort of advanced shellcode that is attacker-centric. So things like staying in memory, staying in process, being able to upload and download files without using command.exe, all these sort of advanced penetration type shellcode. We call those post-exploitation tools. They tend to be interactive, and that's the difference between just like a command.exe shell. So then we're going to talk about all the technology behind that, and then how our implementations, and then basically all of the kind of features it would give to an end user. So all of the cool things you can do. So, do you want to start?
Sure. So we've kind of broken down the exploitation cycle into 3 phases. The first phase that everyone is probably familiar with is pre-exploitation. This is the phase where you're finding a bug, you've isolated it, you've figured out how to trigger it, and now it's time to kind of write the tools that you're going to need to be able to exploit this. Yeah,
the way we broke down, everybody has different terminology for this stuff. We kind of do it time-based. So you have pre-exploitation that could be done months and months before an attack. And then you're going to have like the attack itself, which is exploitation, and that's going to be maybe you're a ninja Navy officer and you've waited like 6 months for this attack window, and whatever. So that's what this is going to be. This is going to be reconnaissance, information gathering, finding a target, and then initializing all of your stuff, getting everything ready, and then launching the exploit.
So then the next phase is post-exploitation, and this is the one that we're going to focus on mostly because it's kind of the area of most interest. Like right now, Spoon said, mostly exploitation technology has matured at this point. We've got all the vectors, determined. We can reliably get code execution, but what do we actually want to do once we can get code execution? So that's going to be this post-exploitation phase of the timeline. This is the phase where everybody's familiar with getting a command shell. Some of the other things like executing commands, file access. If you saw the demo last year, you saw VNC injection, and all these other advanced payloads that you can do during this phase. It's just kind of arbitrary. So we're going to kind of provide a glimpse into some of the powers that you have during this phase of exploitation.
And post-exploitation could go on for a long time. It could go on for days, I mean, whatever you want. It's up to the end exploiter, I guess. And then it could kind of include things like rootkits and stuff like that, but we're not going to talk about that. We're just going to sort of talk about our post-exploitation shellcode stuff. So. Okay. So, I mean, most people hear this term payload or shellcode used pretty much interchangeably. But I mean, back in the day, it used to be just an assembly blob, and things have sort of the typical attack has definitely evolved into something much more advanced, and it might be something you don't even necessarily realize. So, how a payload breaks down, a NOP sled is optional, but it's used for an exploit where your return is uncertain. So generally in Windows exploits, you won't see NOP sleds very often. And there's a lot of IDSs that claim to be able to do NOP sled detection and stuff like that. And that's kind of garbage because for half of the time, for most of the good bugs, you don't even need a NOP sled. But there are some situations, Unix exploits, brute forcing attacks, where NOP sled can be very valuable. So, how it works is control is going to, hopefully you're going to land somewhere in this NOP space. It just gives you a big area to land into. And then it's generally 1 byte aligned, and you're going to sort of run through this and then run into the payload. So then something that's also, you're not going to see this for local exploit and stuff. We generally have, we'll use the term encoder and decoder pretty much interchangeably. So what this does is it's a little stub piece of assembly code that's going to get put before your payload, and it's going to unencode your payload. So basically, before you do an attack, you're going to take your payload, and for reasons we'll talk about, you want to transform it somehow. So say you want to turn it into ASCII characters, say, any sort of encoding, you want to base 64 it or something. I mean, obviously that wouldn't work very well in our case, but any of these sort of transformations. And then, of course, you can't execute that directly. So you need something to untransform it. So this is going to be the inverse operation. And that's just this little piece of assembly code that's going to get stuck before that. So that's the decoder. And then the encoded payload you see in parentheses, that's going to be your end payload, your command shell, whatever that is. And that's going to be encoded when it's sent over the wire. So the payload, this is just our arbitrary code. This is typically, in the generic sense, it provides a command shell. But the stuff we try to do is a lot more advanced than that. So like I said, a NOP sled is going to be a series of bytes that equate to no operations. So basically, when you don't know where you can return into an exploit, you don't know an exact address, but you can kind of get an idea. What a NOP sled allows you to do is allows you to give a very big surface area to land. So you can say, all right, I'm going to try to put like 1K of NOPs, and then I have a feeling I can guess the address within that 1K. So then you're going to land. You could land at the beginning, in the middle, at the end, anywhere in this. And then all it's supposed to do is just be instructions that don't do anything harmful. And then they just run, and then you land into your payload. So it's sort of that's why it's called the sled. It's just you're hitting it, and then you're sliding in to your payload. So a client's just going to build a NOP sled, and it's going to be appended to the payload. And then it's just going to transmit that entire thing. So you can have the payload, and then you're going to have this big sled out front. So then the target is going to execute all, some, or none of the NOP instructions. Just depends where you return, and the idea is that you have this big range that you can hit. So instead of having to guess, an address to the byte, now you can guess an address to the, 1K, which is, a lot more predictable. So then the execution just falls through to the payload. So not all vulnerabilities have predictable return addresses. Pretty much all Unix brute forcing exploits can take very good use of an NOP sled. So it can improve the exploit quality. At the same time, it can it can be bad too, because a lot of people will try to signature on NOP sleds. So on one hand, it can improve the quality of your exploit. On the other hand, it can sort of decrease your stealthiness. You're going to have to send a bigger request to have all these NOP sleds in, and it may be something that's predictable. So, but one thing that having a big NOP sled does is it allows you to brute force in bigger increments. So if you've ever seen a brute force exploit, it'll run us like trying this address, trying this address plus 4, trying whatever. So the bigger the NOP sled, the bigger these address jumps you can take. So if you have a small NOP sled, maybe it'll take 20 attempts before you find the address. But if you have a big NOP sled, maybe you can do it in 1 or 2 attempts. So it's kind of like this trade-off of all of these different things. It's stealthy and at the same time less stealthy, because it's stealthier because now you're making less requests, but it's also bigger requests. So this is stuff that if you guys ever want to do, some sort of advanced attacking, this is stuff that would be important to understand who you're attacking, and then what sort of qualities you find most important in your attack.
That would be kind of during the exploitation phase, during your reconnaissance. You'd kind of figure out would it be best to use a larger NOP sled or a smaller NOP sled, just based on the situation.
Yeah, knowing what kind of defensive mechanisms they have, what kind of people watch their network. Some tools will be very specific to seeing noisy traffic, so lots of connections or something like that, where, and it also depends on, depends on a lot of different things. So existing NOP sled technology, everybody knows OX90, and that's used a lot, even in Core Impact and Canvas, both still use OX90 sleds a lot. So that's very signaturable. ADM Mutate came out a while ago, and they had a single byte x86 NOP generator. And that would use different 1-byte opcodes. So OX90 is just a no operation. But there's other things, setting flags, clearing flags, things that aren't really going to, they do something, but they aren't going to do something that's going to affect the execution. So what we want in a no operation instruction is we want something that's not going to cause harm. It's not going to crash the machine. It's not going to modify any memory state, anything we want to save. So we could do things like, add a number, decremented number, add a number, decremented number. If it's something we don't care about. So Metasploit technology, we're not going to really talk about this, but we have something called OptiNOP2, which is a multi-byte NOP sled generator. So instead of just having 1-byte opcodes, it allows you to have between 1 and 6-byte opcodes and prefixes and stuff like this. So it makes detecting NOP sleds a lot harder, because none of the existing, some people wrote some tools that would detect ADM mutate sleds and stuff like that. And this is really makes things a lot more difficult.
Yeah, just throw it out there. Spoon actually presented at Recon, and his slides talk about OptiNOP2 in quite a bit more detail. So if you're curious about how it works, you can check that out. So the encoders that we talked about, the purpose behind the encoder is we want to retain the functionality of the payload, but we want to transform the way that it's represented in memory, or just as a set of bytes. So how the encoder works, basically, and just to back up a little bit, the reason why you would want to encode is, let's say, many times you'll run into exploits where you can't use a certain set of bytes. You can't use a space, you can't use a backslash, you can't use, higher than 7-bit, opcodes or anything of that sort. So what you can use is an encoder in this case, so that you can transform the format of the payload without actually changing its functionality.
We talk about that more in the slides, I think.
Yeah, so kind of just to breeze through this, basically how the encoder works is on the client side, prior to exploitation, you have a stub that'll process your raw payload, the one that's going to give you a command shell or do any other advanced step. And it's going to encode it and just kind of transform it to the form they're actually going to send across the wire. So before we send it across the wire, though, we decode a decoder stub. And the purpose of the decoder stub is to, once that code is executed on the target machine, to take that encoded payload, transform it back to the original form, and then fall into it and execute it. So we'll see that here. So after we do this, the client's going to transmit the entire payload via an exploit. It's going to get over there. The code's going to get executed. So the target executes the decoder stub, and then the decoder stub is going to perform that inverse operation, get the payload back to its original format, and our code's going to execute as normal.
So an simple example of an encoder. So we say an encoder, and then we usually say decoder stub. So usually there's two components. There's sort of the attacker side. This is going to be something that, if you're using a framework, this is something that's going to do for you. For example, Metasploit. So an example of a simple encoder would be you take every byte and you add 1 to it. So if you had OX40, now you have OX41. And then the counter decoder stub that's going to be written in assembly is just going to loop through the encoded payload, and then it's going to subtract 1 because you added 1 before. So what this is just allowing you to do is take your payload and sort of mutate it into a different byte space. And that has a lot of really important uses. So pretty much most of the all of the stuff you see in Metasploit, if anybody's ever used it, that would not be possible without encoders. They're quite important.
So yeah, just as we were saying, the purpose of the encoders, what's so cool about them is that now you can avoid those restricted characters in your payload. You don't have to worry about having a null byte in your payload. Yes, having a decoder stub prefixed in front of the payload is going to make it a little bit bigger, but oftentimes that's negligible, so you don't need to worry about it. So that's one of the big bonuses.
And oftentimes it's interesting because people will say oh, decoders are bad for size, but then you'll see people who write shellcode to specifically avoid certain bytes. They're like, okay, this is null-free shellcode, or this is OXOA-free shellcode. And you look at it, and it actually ends up being bigger than using an encoder, because our encoder stub may be 20 bytes. But by trying to avoid all of these bytes in your actual, your big payload, you may end up, doing different instructions that add more than 20 bytes in the end. So we'll take cases where someone wrote a special case payload against a certain character, and we can just take, our template already made shellcode, throw it through an encoder, and it ends up being smaller. So this is actually, really good stuff. So.
Yep, so the other big bonus of having an encoder is that you can survive transformations. So if you know that the application that you're attacking is going to, for instance, do 2-upper on the payload that you pass it, you can use an encoder to ensure that your payload is already 2-upper safe. So all of the opcodes or the encoded version is already uppercase, so that when you go through that transform, you will be unchanged.
This also applies to things like Unicode and stuff like that. So there'll be cases where you'll have a buffer. It either has to be in Unicode to begin with, and it gets validated, or it'll get transformed into Unicode. So you're going to need to be able to have a payload that after these transformations are still going to be correct executable machine code. So as a cool sort of side effect, encoders were actually written for very practical reasons. They weren't written for IDS evasion. They were written so we could avoid certain bad characters. And the exploit wouldn't work without avoiding these characters. It would terminate too soon, the overflow wouldn't happen, whatever the case would be. So generally they were written for very practical means. But then sort of as a cool side effect, you avoid a lot of IDS, a lot of sort of IDS stuff. For example, if we have a normal payload, we might have /bin/sh somewhere in here, because we're going to execute /bin/sh. So that string would be somewhere along our assembly code, because it's just going to be data to our code. So now as a side effect, since all of our stuff's run through an encoder anyway, that's going to be transformed, and that's not going to be on the wire anymore. So if any IDSs are trying to look at specific things that are characteristic to a payload, bin/sh, any of these sort of things, now as a side effect, we just we can mutate and pretty much avoid any sort of we can avoid any detection on the payload, pretty much, on the encoded payload.
So just kind of give some background on encoder stuff. The de facto standard at this point that most people use for encoders is XOR, just because of the nice properties that XOR has of giving you a better bit distribution and better possibilities that you can create by doing an XOR on a given byte, word, or D-word basis. So basically, just for those who aren't familiar with XOR, we're not going to cover it, but basically the purpose of this is you have your payload separated into different blocks. It's either a byte, 2 bytes, 4 bytes, whatever the case may be. And what you do is you have a key that's either static or variable that you go through, just loop through every block in the payload and XORing it with that key to generate the encoded version of the payload. So then what you'll do on the flip side is when it's running on the target machine, you'll have the decoder stub that just does the exact same operation. So XOR is its own inverse. You'll get the same result back that you had on the original side. So that's one of the nice reasons that XOR is used, just because of that property of XOR.
And in a framework like Metasploit, not only is the encoded payload being dynamically generated, but also the counter decoder stub is also being dynamically generated. So for example, you just give us a payload, and you're going to say, I want to encode it. And then we're going to look, and you say, I want to encode it, and I want to avoid all of these characters. I want to avoid null, I want to avoid OXOA. And then we have some systems that are going to look through, and we're going to determine a key that when your buffer is XORed will avoid all of these characters. So if you say, I want to avoid this big list, we go through and we find a key that when the data is XORed, it will avoid those characters. So we mutate this, and then we build the decoder stub, and we put that XOR key that we just found in that stub, and we put the two together. So some other encoder and technologies that exist, and in fact are in Metasploit. Well, Rix wrote a good alphanumeric paper in Frac 57 talking about how to sort of do exactly what we're doing except staying in an alphanumeric range, which is pretty hard because you're really limited to the assembly instructions you can use. So that's definitely an advantage of using an encoder to try to change the whole payload, is that an encoder you can just write once, and you can try to make it as small as possible, and then that's it. So so then Rix wrote this paper, and then Skyland came back and did a very good, he sort of improved on a lot of different people's techniques, and wrote a very good implementation of an x86 ASCII and Unicode encoder. And Metasploit has that in it, and it works really well. Davitel and FX also had written encoders for Unicode situations. And that's really important because, I remember when FX and Davitel were first writing these encoders, it was just, one bug came out and your payload had to be in Unicode. And, none of the existing technology was really able to do that. So you have to sit down and you have to think about it and you have to write and try to design an encoder that can, deal with these constraints. So then in Metasploit, we have just a normal encoder called Shikata Ganai, which was written, I guess, mostly for IDS evasion.
Yeah, it's not really that normal. Just to interject here, one of the cool properties, he's the one that worked on this. One of the cool properties of Shikata Ganai is basically what it does is decoders usually, except for the key, are generally static, which is one of the points on there. So this is something that a lot of IDS vendors will pick up on, and they'll say, well, I know that the payload could be encoded, so I obviously can't signature on that. But what I can do is signature on the static decoder stub that's going to be sent prefixed to this encoded payload. So what Spoonm did is he went and wrote an encoder that basically has just the instructions are set up such that they can be moved around or substituted with other instructions of the same length. And he just built some block-based dependencies and things of that sort. So what he can do is, at runtime, he can build a decoder stub on the fly that is functionally equivalent to any other of the decoder stubs that he's going to use, but totally different in format. So you end up with something that is going to be very challenging for IDS people to signature. So that's the cool property of.
And it's also pretty useful for functional reasons, because one of the problems, we keep on talking about avoiding bad characters, which is very important. So what happens when the encoder you're using is a static encoder, it has a bad character? Well, then you have a problem, you can't use that encoder. So that's one of sort of the nice things also about Shikata Ganai, is it was sort of designed to be, to try to be able to generate lots of different combinations with different byte sequences and stuff like that. So you can actually tell Shikata Ganai that I'm trying to avoid, this character. And maybe it would have had it if it was static, but this way, when it generates itself, it tries to look and say, like, okay, I have these 4 possibilities. Well, let's remove any of the possibilities that have a bad character. And now I'm going to pick one that doesn't.
If you're curious about that, that's also in his recon slides, so you can check those out.
We've talked more about the details of this stuff in other presentations. So we won't try to talk about it too much. We'll try to lead into the what's built upon this sort of stuff.
So kind of here, the big question is, what is a payload? And this is something we've already kind of answered, but basically it's going to be the arbitrary code that we execute that does some undefined task. It's totally arbitrary, whatever it's going to do, whatever we can fit into the exploit in this situation. So how a payload works, this is pretty simple. The client prepares the payload for execution. What that could entail is basically you may need to embed the command string, or you may need to embed target IP address and port if it's going to connect back to you, for instance, to give you a command shell. So that stuff needs to be substituted prior to being transmitted to the other side. After that happens, the client's going to transmit it to the target. That code's going to get executed, and then you'll get your arbitrary, whatever it is, whatever your payload's going to be doing.
So does anybody have any questions on any of this stuff yet? Are we going too slow or too fast? It's hard to judge where everybody is on the different scales of this sort of stuff. In what?
The question was, what does Shikata Ganai stand for?
It means like it is inevitable. There's no stopping it. Blah, blah, blah. So it's like you're screwed in Japanese. So.
Yeah.
Well, the thing about that is that repeating the question was, does it try to sort of do any sort of, a lot of IDSs will do disassembly and try to tell if it's valid machine code and stuff like that. And do we do anything to try to throw off disassemblers, any length, trying to like throw off a disassembler so it gets the wrong length of an instruction, something like that? And no. The entire payload is 27 bytes. 4 of those are a randomly generated XOR key, and 4 of those it actually can encode the last 4 bytes of itself. So it's encoded. So there's 19 bytes that are not random. Out of those 19 bytes, there's 1.5 million permutations. So I was just hoping that even if you had a disassembler, only the first 19 bytes are going to disassemble, and that's not really enough to say a lot. Like especially just on normal network traffic, I mean, there's going to be a lot of 19 bytes to disassemble. So, I didn't do anything specific, but I have confidence that that sort of stuff won't hold up for other reasons.
So the question is, what in Metasploit is identifiable?
Yeah, I mean, as anybody who does IDS stuff will know and should tell you that you should try to signature a vulnerability, not signature sort of,
it's going to be a losing
things about a vulnerability.
It's going to be a losing game to try to signature the payload. I can do a million things to make it look a million different ways, and you're not going to be able to signature it. So it's best to try to signature the vulnerability, the ways that it's being triggered.
Right. I mean, it'd be like, the problem is if I give you some bytes and you tell me if it's a program or not, you know what I mean? Like, it could look like a program, but it's not. You know what I mean? Like, a string of A's is completely fine executable code. So, I mean, trying to do these sort of detections, I mean, IDS vendors know that this is not the right way to do it. Sometimes it's the easiest way, but it's not the best way. So, I mean, there's plenty of things in Metasploit that are signaturable, but they're going to be exploit-specific stuff. Where everything we're talking about here is just sort of general technologies. And out of this, I don't really think that there's necessarily that much. I mean, these are all sort of concepts, so there's nothing signature. So some of our implementations might be, but I mean. And that's not our main goal, is to try to be IDS evasive necessarily.
Yeah,
so.
If people are interested in that, they can modify it and add it.
Yeah, so we try to build a framework that allows you guys to do whatever you want in Metasploit. So if your thing is IDS evasion, then you should be able to, add that sort of stuff. So.
All right, so diving back into this, what we're going to do now is we're going to break the categorization of payloads down into 3 subtypes. The way that we've broken it down is you have what's referred to as a single payload. Basically, what a single payload is it's just a self-contained payload. Basically, this is one that's is very task-oriented. It's going to perform a specific task, whether it be connect back to you and give you a command shell, upload and execute a file. It's all going to be one contiguous set of bytes that's going to perform this single task, or maybe multiple tasks.
And this is probably what most people are familiar with.
Yeah.
If you just see like a big shellcode blob and like a C exploit or something, this is going to be a single payload. Everything's all inclusive. Maybe it gets encoded or something, but it's still just one.
Yeah, it's definitely the most common. The next type of payload that we have is what's referred to as a stager, and this is actually 2 parts. So basically what a stager is instead of trying to do everything in one single blob of opcodes, we split it up so that we have what's referred to as a stager, and this stager is going to be nothing more than a means of loading another chunk of assembly. And the way that it loads that other chunk of assembly is arbitrary. It could load it over a connection, it could load it over any sort of means.
It's not necessarily assembly either. Like if anybody's seen download and execute shellcode, where you just give it a URL and it'll go download and execute it, that would be an example of a stager. It's sort of, it doesn't have the task in it. Its job is only to go get something else.
All right. Right. So, and then the complement to that is you have the stage. And the stage is the thing where in the single payload, we're task-oriented and we have a specific task that we're going to be performing. In the stage, we do perform that specific task. So, for instance, the nice thing about this is the way that it's set up is the stager, if it does establish a connection, it's going to pass that connection to the stage so that the stage can reuse it, use that for socket I/O, talking back to the client for whatever it needs to do. So if it's redirecting a command shell back to the client, it'll use that already established connection. It won't establish a new one on its own.
So the stager, in order to read this more code that we're talking about, this stage, it needs to make some sort of communication back to us.
Yeah.
So that all that's allowing us to do is, since this communication is already established, we can just reuse it in this stage. So it's sort of abstracting the two things. Like we no longer have, a bind command shell. We have a bind stager and we have a command shell stage, and they know nothing about each other.
This also helps reduce code duplication. So if you're writing a payload to do a command shell, and you want to be able to get that command shell over a port bind, reverse, find sock, whatever the case may be, you're going to be duplicating that code to create that command shell for each one of those payloads, even though your connection medium is different. So by separating the two, making the connection medium independent of the stage, you just reduce the amount of code duplication that you're going to have in the end. You just have one command shell stage that uses an arbitrary stager